Hey everyone, and welcome to this explainer. Today, we're bringing you a super simplified guide to something that honestly sounds incredibly complex at first, but is actually the hidden magic behind almost everything you use on a daily basis. We're talking about CNC machining. I am so thrilled to guide you through this because we're going to completely demystify this technology step by step. By the time we finish up here, you're going to look at your smartphone, your car, even your kitchen appliances in a totally different light. We'll be breaking down exactly how raw metal and plastic get turned into perfectly shaped, everyday products. Let's dive right in. To start us off, I want to pose a pretty massive question to you. Take a second and just look around you right now. How exactly do we make millions of completely identical pieces of a product? Think about the perfectly smooth metal casing of your laptop, or the deeply intricate parts inside an airplane engine. Now, human hands are incredibly creative and wonderful, but let's be real. If I asked you to carve the exact same shape out of a block of metal a million times in a row, you'd go crazy, right? You just can't perfectly achieve micromillimeter consistency over a million tries. The human hand shakes, we lose focus, we get physically tired. So how does modern industry actually solve this puzzle? Well, here is our roadmap for the explainer to figure that out. First, what is programmed manufacturing? 2, why do we use these machines? 3, the basic machine parts. 4, how does it move? 5, control and power systems. And finally, a summary. All right, section 1. What exactly is programmed manufacturing? You'll hear the acronym CNC a lot, which stands for Computer Numerical Control. But honestly, let's just ditch the complex jargon right now. Put simply, CNC is just the automated control of machining tools using computers instead of manual human labor. You can think of the CNC machine as a highly skilled, incredibly smart, automated craftsman. Instead of a person standing there turning a wheel or pulling a heavy lever to cut into metal, a computer program feeds specific, step-by-step algorithmic instructions to the machine. It literally tells it exactly where to go, how fast to move, and exactly how deep to cut. And I love this because it perfectly illustrates the core equation of this whole concept. Think of it like this. You have the computer and its software. That's the brain. Then you have the actual machining tool, like a spinning drill or a heavy-duty metal cutter. That's the brawn. When you combine the brain of the computer with the brute brawn of the machine tool, boom, you get CNC. You get a mechanical worker that knows exactly what to do and has the physical power to execute it flawlessly every single time. Moving right along to section 2, why use CNC machines? Let's talk operational benefits. The answer really lies in their incredible operational advantages. First up, they offer unmatched precision. We are talking about accuracy down to fractions of a single millimeter. Second, error-free accurate repetition. You can hit start 1,000 times, and I guarantee the 1,000th part will be absolutely identical to the very first one. Third, there's a massive reduction in human error. Like we said earlier, machines don't need coffee breaks, they don't get distracted by their phones, and they don't get physically tired. And fourth, they can create super complex shapes and geometries that would be virtually impossible for a human to carve out by hand. When you put all those benefits together, it's a total game changer. You've got that micromillimeter precision locking in perfect targets. You've got repeating cycles allowing for massive, perfectly uniform mass production. You completely remove operator fatigue from the equation because the algorithms take over the heavy lifting. And because of that, engineers can dream up these incredibly intricate, sweeping designs, like complex turbines or aerospace parts, knowing the machine can actually build them. Section 3. Let's look at the basic machine parts. So, what does this mechanical craftsman actually look like on the inside? Let's walk through the anatomy. First, you have the monitor and control panel. That's the actual brain of the operation where the operator feeds in the instructions. Then you've got the spindle. The spindle is basically the machine's hands. It rotates at impossibly high speeds, holding and driving the cutting tool right into the raw material. Next is the tool magazine. Imagine this as an automated toolbox that literally spins around and swaps out different drills and cutters in the middle of a job with zero human intervention. Pretty wild, right? Finally, there's the work table, which acts as a super sturdy desk, tightly securing the raw block of metal or plastic so it doesn't budge even a fraction of a millimeter while it's being carved. All right, section 4. How does it actually move? Before we visualize the machine in action, let's compare the two main ways it moves. It's actually really easy to grasp. The first is called point-to-point. Imagine you're jumping from one distinct spot to another to do a specific task, like drilling a hole, pulling the drill out, and jumping over to the exact spot for the next hole. The second type is called contouring, and it's totally different. Instead of jumping around, imagine ice skating. You're making a continuous, smooth, flowing cut along a highly calculated path to carve out a complete shape. You can really notice the difference when you visualize it. With point-to-point motion, the drill moves to distinct numerical coordinates. It goes down, drills a hole, goes up, and moves over to the next point without doing any cutting during that transition. It's very stop and go. But with contouring, the tool stays deeply engaged in the metal the entire time. It cuts continuously along a multi-dimensional path. This continuous engagement is absolutely crucial when you need to mill complex sweeping profiles and smooth curves. Now, to make those incredibly sweeping cuts, the machine needs the freedom to move around. Let's talk about axes. Imagine moving around in a 3D space. A basic 3-axis machine can move left and right, forward and back, and up and down. That covers most of your basic shapes. But modern engineering takes it way further. Advanced 5-axis machines do all of that, plus they add rotational axes. This means the cutting tool can tilt, twist, and rotate to approach the material from practically any angle imaginable. It's literally like giving the machine a highly flexible human wrist. Section 5. Control and power systems. Simply put, a machine is honestly only as good as the power driving it. Generally, CNC machines use highly precise electric servo motors to drive the cutting tools. Electricity is the industry standard here because it delivers high-speed, absolute pinpoint precision. But sometimes precision isn't the only thing you need. Sometimes you need pure brute force just to hold a massive block of heavy steel in place while it's being cut. That's where hydraulic and pneumatic systems step in. Think of pneumatics like the power behind that loud hissing sound you hear in an auto mechanic's garage. They use pressurized fluids or compressed air to deliver massive, unyielding clamping power that electricity alone just can't easily match. Okay, so here's a fun question. How does the machine actually know it moved to the right spot? Think of control loops using this simple analogy. An open loop system is kind of like trying to walk to your refrigerator with your eyes completely closed. You take 10 steps, you think you're there, but you might have drifted and bumped into a chair. You have no way to verify. A closed loop system, however, is like walking with your eyes wide open. You are constantly looking around, getting feedback, and adjusting your steps to make absolutely sure you land exactly at your destination. And that concept plays out perfectly in these machines. In an open loop setup, the brain sends a command to the motor and just assumes the motor did its job perfectly. If the tool slips on some hard metal, the brain doesn't even know. But in a closed loop system, there is a position sensor acting as the eyes. It continuously reads the tool's actual physical position and feeds that data right back to the brain in real time. If the tool is off by even a fraction of a human hair, the controller instantly corrects it. That constant feedback loop is what guarantees supreme, unshakable accuracy. Finally, Section 6. Let's summarize this modern technology. Let's zoom out and put all these puzzle pieces together. By understanding these variables, the physical structure, like the spindle and the tool magazine, the heavy-duty power systems, the incredible multi-axis motion, and those hyper-accurate feedback loops, we see exactly how modern engineers leverage CNC technology. It's not magic anymore, right? It is a highly controlled, brilliantly automated workshop that takes raw, boring blocks of metal and transforms them into the impossibly precise components that literally power our modern world. Which brings us to our final thought. Now that you understand the smart, automated craftsmen working tirelessly behind the scenes of our manufacturing industry, I want to leave you with this. How will this invisible yet totally vital technology shape the future of the products you use every single day? Because as these machines get even smarter, faster, and more precise, the possibilities for human innovation are just limitless. The next time you pick up an everyday object with perfectly smooth curves and exact fits, I really hope you take a second to appreciate the beautifully programmed craftsmanship that made it possible. Thank you so much for joining me on this explainer. Keep learning, keep wondering, and I'll catch you next time.